Sorry for the delay. I have done this before, but you wouldn't think it. All right. Well, when we last talked, we had talked about enolate. Now the Apple Pencil doesn't want to talk to the iPad. Okay. When we last met, we had talked about the problems with enolate alpha alkylation. You recall that our typical strategy involves, or our cheap strategy without using LDA involves a base that's only going to partially, only a small amount, deprotonate this carbonyl compound. And so when you go to alkylate the alpha carbon, you have to deal with the potential undesired ether formation side reaction where your ethoxide base acts as a nucleophile and does SN2 on the alkyl halide. But if you pretend that that's not an issue, you can get the monoalkylated product. And then under reversible enolate formation conditions, you can hope that it works again the second time. Here you have to trust in the potential for regioselective removal of the purple alpha proton and then installation of the alkyl group on that purple alpha carbon. And again, that presupposes that you're pretending that the competing SN2 reaction is not an issue. It also presupposes that there's a huge amount of regioselectivity whereby you're able to alkylate only the alpha carbon, the purple alpha carbon, and not the orange one. Now, we're going to pretend that that works, but as a matter of practicality, sometimes it doesn't. So your text presents a workaround, and we talked about this. I showed you this beta keto ester, which has particularly acidic purple alpha protons, so acidic that even our weak and cheap base sodium ethoxide can remove the alpha proton to make the enolate at 100% yield. And therefore, in the second step, when you do alkylation, there's no sodium ethoxide base left, only enolate. And then it's trivial to alkylate at that alpha carbon. And you can stop there if that's your desired product, or you've got a second alpha proton that's also acidic, which you can remove with another equivalent of sodium ethoxide and then alkylate again on the alpha carbon. So here is our temporary product. Our goal is to make this acetone derivative that's dialkylated on one of the alpha carbons. And I told you, though we paused before we got there, that this is masked acetone. And so what I want to show you now is how you can unmask the desired product. What we're going to do is get rid of this ester group. But in so doing, we're going to demonstrate something that's important and comes up multiple times in 352 and again in biochemistry, and that is called the concept of decarboxylation of beta keto acids. Before we do that, any questions you have on what we're doing here with that dialkylation? Okay, just as a preview, some of you will hate this, but sometimes we do this reaction and the two alkyl groups are actually attached to each other to make a ring. That's a fun way to make a problem that looks straightforward a little bit less straightforward. And I'll show you an example of that in a little bit. For now, let's talk about how we unmask our dialkylated product to get to something that looks like that ketone. So we'll call this the unmasking process. So unmasking proceeds in a couple of phases. One reaction, you need acid and aqueous conditions. H3O plus just means aqueous acid. And you need heat, which, as you've learned in OChem, we show with a triangle because it looks like a fire. And what this does ultimately is it gets rid of the ester and gets you that desired product. So let's talk about what happens to the ester, because right now that looks like magic chemistry. The first thing that happens to the ester is, under aqueous acidic conditions, that's ester hydrolysis, right? So you have seen the mechanism for that in chapter 16, though it may be worth a little bit of review. I'll just summarize what's going to happen as first ester hydrolysis, then decarboxylation, and then lastly tautomerization. So you've seen two of these three things before, but not necessarily the decarboxylation. So when we do ester hydrolysis, what's the first thing to happen? We want water to attack the ester carbon, but first we have to protonate the carbonyl. Good. We'll do that with our aqueous acid. Generally, water is not a good enough as a weak nucleophile, not a good enough nucleophile to attack the ester carbonyl oxygen. So we protonate to make the oxonium ion. Then water can attack. This is typical nucleophile, attacks a carbonyl carbon. That's going to give us a tetrahedral intermediate. Except too many bonds to carbon. That's better. Now, because we want to hydrolyze the ester, ultimately we want this OET, the ethoxy group, to be the good leaving group. Right now, water is the good leaving group, so we need proton transfer using the conjugate base of our acid to change up who's the good leaving group. Okay, now we've got this neutral intermediate. We're going to protonate the ethoxy group. Thereby turning it into a good leaving group. Then we've got that classic situation where we have a good leaving group, and then here's the alpha position, and then beta to the good leaving group. On either of those oxygens, we've got lone pair electrons that can kick off the leaving group. It's perfectly fine for a neutral oxygen to kick off a neutral leaving group. Oops, kicked it off but forgot to have it leave. And somewhere along the line, somebody was going to point out that we lost methyl groups, right? Sorry. All right, so that's where the ethoxy group from our ester ends up. It leaves as ethanol. Here's where we've converted it into a good leaving group, and there's where it leaves. So that was ester hydrolysis. And this gives us something that's called a beta keto acid. Carboxylic acid, carbonyl carbon, alpha carbon, beta carbon. When you have a carbonyl beta to an acid, you are set up for decarboxylation. So let me show you, we'll need to redraw that beta keto acid. So this is the ester hydrolysis phase. Now we're going to do the decarboxylation phase. But before we do that, that should have been reviewed. You've seen that before. Any questions that are remaining on that? Sure.
Where did the OH go in the, like...
Yeah, I'm sorry about that. Weren't quite there. I skipped a step, didn't I? Actually, right. When the ethanol leaves, you get not the beta keto acid, but the corresponding oxonium ion. Thank you. And then in the final step, we restore the catalytic acid by removing the proton from the positively charged oxygen. And that should get us there. Thank you. Sorry about that. Okay, others? Anything else you noticed? Okay. Let's talk about the beta keto acid, and we'll redraw it. I'm going to draw it in a way that makes the decarboxylation reaction easier to draw arrows for. What we're going to do is actually just rotate around the bond between the alpha carbon and the carbonyl carbon such that the OH is here. Okay? And this puts the carbonyl oxygen, or sorry, this puts the proton of the acid very close to the carbonyl oxygen of the beta keto group. And what we can draw next is a series of 3 arrows that can happen anytime you've got a carboxylic acid adjacent to or beta to a ketone. That is, the proton is probably already hydrogen bonding with that beta keto carbonyl group. So it's not such a stretch to think that it would pull off the proton entirely. Electrons can kick down to form a new carbon-oxygen pi bond. The electrons between the carbonyl carbon and the alpha carbon kick over to form a new pi bond between the alpha and the beta carbons, like this. And then the pi bond between the beta carbon and the carbonyl oxygen breaks. And this process is irreversible because your carbonyl carbon ends up leaving as CO2, which bubbles off as a gas, and that's an irreversible process. For right now, I'm going to continue to label the carbons the way they were in our starting material. We have a new pi bond between alpha and beta carbons here. We have a new sigma bond between oxygen and hydrogen here. And then I guess we have a new carbon-oxygen pi bond there. Okay? So that's the decarboxylation step. It's called decarboxylation because we lose CO2, and that's irreversible. And this can happen anytime you have a carbonyl carbon adjacent to a carboxylic acid, or beta to a carboxylic acid. And the reason it works is because if you follow along as CO2 leaves first, the beta keto oxygen provides something to deprotonate the carboxylic acid. Second, as the carboxylic acid leaves, there's a place for the electrons to go. The electrons from the carbonyl carbon alpha carbon sigma bond can come over here and make the new pi bond and then go onto the oxygen as a, and the pi bond between carbon and oxygen can go out onto the oxygen as a lone pair. Okay, decarboxylation. That's, I think, the first time you've seen that. When we get to our chapter on metabolism, that's going to happen a lot. In fact, a lot of the CO2 you are breathing out comes from decarboxylation of intermediates that are kind of like this. Okay. Questions about decarboxylation? Yeah.
So, are you ever going to have like a bottle of beta keto acid, or are they so unstable that it'll always keep it exposed?
It's a good question. Can you bottle a beta keto acid and is it stable? I don't know actually how much you have to heat it up before the CO2 comes off. Probably not a ton, but yeah, the question of shelf stability is a good one that I just don't know the answer to. Yeah, what else? Same question? All right. Yeah.
There were a couple examples in the textbook where decarboxylation like looked a lot different than this. Like something would get deprotonated up here, and there were like 6 different arrows that kind of trickled down to the bottom of the molecule. Is this usually what it would look like for us when we're doing it? Sorry, that didn't make any sense.
No, that's okay. I just didn't have, the question is that in the text, it looked like decarboxylation was different, and
I just remember one example that looked just like this in the textbook, and then there was one that was kind of funny looking, but I can't remember
okay.
what it was. So that was
I'm looking at the text right now under decarboxylation. I'm seeing one difference that's inconsequential. I'll try to illustrate that here. Here I showed the carbonyl oxygen deprotonating with lone pairs, and then I showed this arrow coming up onto the oxygen separately. In your text, I still like that and will probably continue to leave it that way in my notes, but it's pretty equivalent in your text to do this. So just have the pi bond between the carbon and the oxygen breaking and have that do the deprotonating instead of the lone pair on the oxygen. The reason that's equivalent is because the pi electrons, as this carbon oxygen pi bond is breaking, those end up on the oxygen as a lone pair. We can't actually tell which lone pair on the oxygen does the deprotonating. So it's fine. Conceptually, I like it a little bit better. It keeps things stepwise, or it keeps things sort of sequential. We deprotonate first, and then everything else happens. So those are 2 different ways you can do decarboxylation. I am looking, but I'm not seeing necessarily anything else. There's something else I could say that is also true, but probably wouldn't help, so maybe I just won't. Yeah.
So this is within the same molecule, but can we have something else deprotonating, and then the oxygen on the beta carbonyl probably have protons somewhere else?
Oh, okay, yeah, so I think your question is, what if somebody removed a proton from the carboxylic acid first? Does the deprotonating have to be internal? No, and this is actually the true thing that I was not going to say, but which now you've asked, so I'm going to say it. You can actually do decarboxylation of beta keto acids under basic conditions as well. You remove the proton, electrons kick down. The only difference is when you do that, you do make CO2, and then the thing that's left is, unsurprisingly, an enolate that's resonance stabilized. I actually like this because it demonstrates, this is terrible penmanship, but I'm just going to erase it anyway. It demonstrates why decarboxylation works, because you can think of what's going on here as a negatively charged oxygen kicking off a leaving group, and the leaving group is an enolate. Here's the leaving group, and I'm going to get rid of that alpha carbon now because it's no longer, label it, no longer helpful to us. But similar to how we did things in carbonyl chemistry when we had a tetrahedral intermediate, you got a leaving group, this carbon, and then sort of beta to the leaving group, you've got kicker-offer electrons, and that's sort of what's happening here. Yeah. So that view is fine. You can actually do decarboxylation under basic conditions. In the malonic ester synthesis, you do ester hydrolysis under acidic conditions, and then you decarboxylate. We'll stick with those conditions following the text pretty closely, but in the future, if you want to anticipate when decarboxylation is a possibility, just be looking for an acid, a carboxylic acid with a carbonyl group on the beta carbon. And then the potential for decarboxylation can happen under both acidic or basic conditions. I'll show you some examples of that in some biological contexts in a little bit. Other questions? Okay. So we've done trying to get rid of that. We've done 2 of our 3 things. We've done ester hydrolysis, we've done decarboxylation. Now we've got to do tautomerization. Compare where we are here to where I said we were going here. That's the ketone. We're in the enol form, right? And so lastly, we just need to tautomerize from the enol form to the keto form. You've seen tautomerization before. You can actually do tautomerization under acidic or basic conditions. For this synthesis that we're doing, it's under acidic conditions. So the best way to do the tautomerization is this. Here's the acid. We're going to protonate on the alpha carbon. So now that we've got this enol, this is the carbonyl carbon, this is the alpha carbon. You can show this in one of 2 equivalent ways. One way is simply to have the pi electrons from the carbon pi bond attack the proton, protonating. You're going to choose selectively to protonate on the alpha carbon. And that, if you draw the arrows this way, that will leave a positive charge on the carbonyl carbon. Of course, what I just showed you is fully equivalent to the following alternative, which would be to have electrons on the oxygen kick down to form a new carbon-oxygen pi bond, and then to have the carbon-carbon pi bond attack the proton. The reason I'm telling you that what I just drew is fully equivalent to what we drew above is that the 2 outcomes are resonance structures of each other. So you are welcome to draw tautomerization either of those 2 equivalent ways. No real difference between the 2. What we just did basically establishes puts the carbon-hydrogen bond in the right place. What's remaining after this is either on top to remove the proton and have electrons kick down and form a carbon-oxygen pi bond, or alternatively, as shown below, you can simply deprotonate the oxonium ion. Either way, that gets you to the ketone product. Okay? So that's a lot. Of course, synthetically, it's simple. It's one step. Add water and acid and heat, and boom. Mechanistically, you got a lot of things to do there. You first hydrolyze the ester. Second, decarboxylate. And third, tautomerize. Okay? Questions about the mechanism? All right, so this now is going to push you on your thinking backwards synthetic skills, because you need to look at something like this and say, I could have made that. Sorry, look at something like this and say, I could have made that from this starting material, which looks nothing like it. Okay? So how do you do that? Well, there's some structural patterns to recognize. Look at that starting material. The carbons that have been highlighted in purple in the starting material are all in the product. So let's think about that product and think about how we might recognize that as something that could have come from that starting material. And I'll just redraw the starting material here. We call this starting material acetoacetic ester, or alternatively a beta keto ester. A key structural feature of the beta keto ester is this methyl group, which is basically a spectator for the whole reaction. Your product is an example of what I'm going to call a methyl ketone. That is a ketone in which one of the two carbons attached to the carbonyl is a methyl group. That's a structural feature indicator. If you see a methyl ketone, you should be thinking, I could have gotten that from acetoacetic ester using alkylation chemistry followed by ester hydrolysis, decarboxylation, and tautomerization. All right. So let's do one of these in a retrosynthetic sense. I'm going to draw you a methyl ketone product, and then you need to figure out what the starting material was. Not only what the starting material was, because I'll give you a hint, the answer is this. That's not hard. But then what were the alkyl halides that I used to get there? In this case, look at the methyl ketone, ignore the methyl carbon, go to the other alpha carbon, and then pay attention to what groups are on that alpha carbon. 2 methyl groups. That tells me somewhere along the way I did alpha alkylation of this starting material acetoacetic ester, and I did it twice. And here I must have done it twice with the alkyl halide methyl bromide. Okay? So, all right, let's think retrosynthetically. Now, I know that there's something, years ago there was a cartoon called SpongeBob. You guys know SpongeBob? I never really watched that much of it, but you can look it up on YouTube. There's this scene where somebody asks SpongeBob a question, and then it zooms into his brain, and you have lots of mini SpongeBobs running through the brain, rifling through filing cabinets, looking for information, and everything's on fire. And I know this is what happens to your mind when you see a ring of any size, particularly when your starting materials didn't have a ring in it. Okay? So let's figure out how to what you need is some kind of fire extinguisher to put down all the flaming SpongeBobs to allow yourself to think clearly under situations. So let's figure out how you're going to do that. First, you're going to recognize that this is indeed a methyl ketone, right? So that's going to clue you in to the idea that your starting material could have been this acetoacetic ester. That's the easy part. Now, if you want, we can think backwards in sort of a stepwise way. What does this look like immediately prior to tautomerization? Compare it to what you saw before, and then tell me how to draw the enol form of this methyl ketone. It's an enol, so there's an OH group. Where should my carbon-carbon pi bond be? Towards the ring, right? That's not to say there's not another enol that could form. That's fine, but we're thinking backwards along the pathway that led from our starting material to our product. Okay. So that's the enol form. Here's another tough part. Let's think backwards through the decarboxylation. Here, it might be helpful to realize that the carbon that bears the oxygen used to be our beta carbon, and the carbon to which that beta carbon is doubly bonded used to be the alpha carbon. Did I get it wrong? I totally got it wrong. There we go. Beta, alpha. Okay. So let's draw what it would have looked like prior to decarboxylation. At that stage, we lost CO2. So tell me where and remember the precursor to decarboxylation is a beta keto acid. So tell me about that. What should the beta carbon be? What should the alpha carbon be? And tell me where the acid is going to be. Somebody say something, or I'm going to throw the Apple Pencil to a random student who I'm going to make come up here and draw. Is that a threat? Are you threatening me, Master Jedi? What do you got? Anything? Well, I'll give you a hint. The beta, where the enol oxygen is, that used to be the keto group. Now where's my acid going to be? Alpha carbon. I just lost the ring. Where did the ring go? It's on the alpha carbon. Okay. Good. All right, let's think backwards through ester hydrolysis. This one should be easy. Where is the ester going to be? Right where our acid was. Okay. Based on the fact that none of you were saying anything, some of this was not obvious, so let's talk through that. What jumps are confusing? Don't be shy. Decarboxylation, that jump was confusing, okay? Maybe it would help to go through it forward. see it forward, and then maybe it will be a little bit clearer how we got where we ended up. For decarboxylation, it's easiest to draw the mechanism if you draw the acid group like this, with the OH on the carbonyl carbon, or I'm sorry, on the carboxylate group pointing towards the adjacent beta keto group. Here, again, that is a structural pattern you're going to need to recognize as when decarboxylation can occur. And the pattern there is beta keto acid. And also notice that the atoms that are going to be involved in this process, there are 6 of them. They're close to each other. This is sort of what we call a 6-member ring transition state reaction. Lone pairs on the oxygen remove this proton. These electrons kick down. These come over to form a pi bond between alpha and beta carbons, and then the carbon-oxygen pi bond breaks and moves out onto the oxygen. That gives you CO2 and then the enol. So there are 2 products to decarboxylation. You've got CO2 and the enol. All right, there. So how can I help you see how to think backwards from just seeing the enol? Because if you're thinking, anyway, if nobody draws for you that CO2 was there, you're going to have to remember that you could have gotten this enol from decarboxylation of this acid. Yeah?
I think some of us were a little confused about how the 5-member ring got on the acetoacetic ester in the first place.
Okay, good. We didn't do that yet, which is, and what you're asking is, how did we get this here
'Cause I feel like
from there?
Like, naturally looking at that, you're like, oh, the ketone like the oxygen should go on like that pointed tip of the 5-member ring, but it doesn't because we lose CO2. So I feel like some of us were stuck there.
You were thinking that the oxygen should end up here?
I was just like, I didn't think that, but I could see how
Okay.
easy it is.
No, that's, you know that it's true that when you're thinking backwards to decarboxylation, the way this is drawn, it looks like maybe you could just put an oxygen there or something. But no, look at your enol. Again, find the methyl group. When you do the decarboxylation, it's as simple as saying the acid needs to be attached to the alpha carbon, independent of whatever else is there. All right. If that's not, anyway, what else? I mean, what do you, follow-up question on that? Something I can, anyway, other remaining things that are unclear about that decarboxylation? I realize it doesn't help for me to stand up here and act like it's obvious, because it's not when you're learning it for the first time. So, what's not clear? I mean, we can use a highlighter. This portion of the molecule comes off as CO2, and this portion comes off as enol. Okay. It may take you drawing through this mechanism a couple of times to see how it works. I'm happy to talk about it, happy to answer any questions if you think of any. Should we talk about how, I'm worried because I don't think this step makes sense to you, but I'm also worried because sometimes when things don't make sense, you're not even sure what question to ask, and I'm concerned that that's where we're at. Yeah, go ahead.
I think we just have to practice it.
All right. Go ahead.
Could we perhaps look for an example of
Yes. I got ambitious. We went too evil too quickly. Good. Oh, whoops. All right, we're still working on thinking backwards, so we're going to do one that. Shame on me. I started your mental SpongeBob's on fire without giving you a sufficiently high-grade fire extinguisher to deal with them. Okay, here is a different enol. And I want you to think backwards through decarboxylation to what the starting material would have been. But I'm going to show you the CO2. So if you're told to think backwards, you've got an enol, you know that it was a decarboxylation, so that means you know that some of your starting material left is CO2. Here's how you piece it together. The carbon of CO2 becomes the carbonyl. Understand that here's something that may help. The previous step, or rather the starting material for decarboxylation, is going to be some kind of beta keto acid. That is a carboxylic acid with a ketone on the beta carbon. Always. That's a structural pattern that you can memorize. The carboxylate carbon of that beta keto acid is going to end up as CO2. The current carbonyl carbon of your enolate used to be the beta carbon of the beta keto acid. The current alpha carbon of your enol, used to be the alpha carbon of the beta keto acid. So to stitch it together, what you do is you simply draw a beta keto acid that looks like this. The fact that there's the methyl group on the enol coincides with the methyl group here. Here is the carbon that ends up as CO2. Here is the alpha carbon that ends up as the purple alpha carbon of your enol. And then here is the beta carbon of your beta keto acid that ends up as the carbonyl carbon of your enol. And now what am I missing? I'm thinking backwards. What else do I need? Had something on that alpha carbon, right? So it's a 1, 2, 3 carbon unit. 1, 2, 3. Okay. Good. Yes?
So it doesn't need to have like 2 carbon chains coming off of that alpha carbon. It can
No,
just be
it can have any number of, yeah, you can have 1 or 2.
1 or 2.
Yeah. Okay, we're going graded steps of evil. But Dr. Doofenshmirtz evil from like Phineas and Ferb. So not like real evil, but just sort of annoying evil. Here's your enol. Here's your CO2. You get less help from me on this one. Draw the beta keto acid starting material prior to the decarboxylation step. And let me know when you got it. in education, this is what they call active learning, which is where I give you something to do and then you do it and then we reconvene. But we all look kind of bored, so maybe it's not active learning, maybe it's just learning. Got anything? Your answer should have a beta keto acid, which you can draw any number of ways. Doesn't matter who's on the right or the left. Okay, what else? Actually, for the sake of like not, let's draw the acid group on the left, since that's how I chose to draw where CO2 was. Okay, what am I missing? The two alkyl groups on the on the alpha carbon. How did you know there were two there? Look at what's on the alpha carbon of your enol, which used to be the alpha carbon of your beta keto acid. Good. And remember, in thinking through this, the carbonyl carbon of your enol used to be the beta carbon of your beta keto acid. And the carbon of CO2 used to be the carbonyl carbon of your beta keto acid. All right. Now are you ready for this again? Let me tell you a secret on that. Ignore the ring. It's totally fine if the ring stresses you out. It's totally fine. What I'm going to show you is the equivalent of saying la 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 la, I'm not listening. No different. We're just sort of sidestepping the panic there. All right, so do you see now that the precursor prior to decarboxylation, again, carbonyl carbon, alpha carbon used to be the carbonyl carbon of my beta keto acid. Carbonyl carbon of my enol used to be the beta carbon of my acid. Draw the beta keto acid, then pay attention to the two alkyl groups, one or two alkyl groups on that alpha carbon. The only conclusion you can draw is that it should be like that, which then you can go back and say it's like that. All right? Okay, good. So that got us to here. We still need to get back to the beta keto ester starting material. So what we've done is we've thought our way backwards through the tautomerization, decarboxylation, and ester hydrolysis. We've gotten to this way station along our synthetic pathway. This is an alpha-alpha dialkylated beta keto ester. Our starting material was a beta keto ester. So we now need to think backwards through this synthesis to see how we got to here from here. Okay, what we're working on, we've already been through the forward direction of this synthesis and the mechanism. What we're working on is thinking backwards so that when you see a problem that says, what starting materials would I have used to make this product via the acetoacetic ester synthesis, you've got tools for dealing with it. We've helped you so far get to where you can start with a methyl ketone and think backwards to the appropriate beta ketoester. We're almost there. Now we just need to think backwards through those alkylation steps to what the starting material would be. Let's take 5, and then we'll pick that up after the break.